Thank you. Good afternoon. Thank you for staying with us, also after lunch. I would like to, in this talk today, I would like to discuss about some of the activity that we've been doing in the past 2 or 3 years about using machine learning to study interacting many-body quantum problems. I will discuss some of the generality of this learning framework, and I will also discuss some of the very latest unpublished results that we have in some interesting applications. So you've already seen, sorry, this is a bit fast, but so you've already seen this morning a lot of introduction about quantum physics, but I guess it's not like too bad if we go through that again. So as a little refresher, in this talk I will be interested in I will discuss a slightly simpler, easier setup in the case where I have just a pure quantum state. So you know that in quantum mechanics, so the problem with quantum mechanics, if you want, is that an easy object, something that classically would be very easy to describe like a spin that can be either up or down, in the quantum realm can be a little bit up and a little bit down, and this is quantified by the wave function. So the wave function, it's a vector. In this case, in this two-dimensional space, if you have just, let's say, the electron, the spin of an electron, and basically all the properties of the wave functions are quantified in terms of these two coefficients. So that basically tell us, for example, what is the probability of observing the system in the up state or in the down state. So these are complex value coefficients. Their square sums up to 1. And the probability of observing the spin in the up direction will be just given by C up, and the probability down is C down, okay? So this is all very nice and easy, so it's for one spin. Now, the problem, as you've heard already before by Juan, is that when you have a lot of these quantum particles, the wave function becomes immediately more complex. For example, if you want to quantify exactly, again, all the properties of a many-body quantum system, in this case, just in the simplest case of n spins, basically you would need to specify all these coefficients here, right? In this, again, so the vector in this Hilbert space, actually in this case it's a finite normed L2 space, but we call it Hilbert space anyways. Basically these coefficients are all you need to quantify the properties of the system. Again, these are complex valued, but these are 2 to the n, right? And you know, the way to determine these coefficients is typically, I mean, in some applications, through Schrödinger's equation. So this is really like the fundamental equation in quantum mechanics. And you know, for the non-physicists in the audience, basically this is nothing but an eigenvalue problem. So an eigenvalue problem where I want to find a vector, psi, my wave function, that is an eigenstate of this Hamiltonian H that you can see just as a linear operator. So basically, like in this case, it's just a matrix, an Hermitian 2 to the n times 2 to the n matrix. So we are typically interested in most applications, not all of them, but often we are interested in finding the lowest eigenvalue of these operators. And as one was already pointing out this morning, the problem is that if we don't make any approximation, but we just want to store this object, so the best way, I mean, the way that I like to describe this is that basically, if we had to consider during the whole history of humanity how many qubits we could store using the best storing technology that we have, basically in 5,000 years, so starting from the Egyptians, we have managed to go from the 10 qubits that you can write down on a piece of paper, basically, so all the coefficients that you can write on a piece of paper, to what you can store in the largest supercomputer these days. So this is a rough estimate, and basically in 3,000 years we have improved by 5,000 years by a factor of 5 in the number of qubits that you could store in the best state-of-the-art storage that we have, right? So it's clear that, you know, this exponential complexity is there. We cannot avoid that. However, the question which is very relevant, and that again is related to what Juan has said this morning, is this complexity truly exponential for physical systems, right? So it's clear that in theory this exponential is there, but you know, as computational scientists we like to deal with NP-complete problems and worse. So we'd like to understand if we can try to beat this complexity, at least in interesting cases that we like, right? So, and one of the way around that people have used during the past, or no, they still use a lot during the past, is, for example, when you have a Hamiltonian that is that has some special properties such that, in particular, it's called stochastic Hamiltonian. So the matrix elements are have a definite sign, and in this case, you can define through a path integral mapping an approach where you never store, for example, to find the ground state, an approach where you never store the state, but you just sample from it doing a stochastic process, right? So in this case, when the wave function is positive, you can devise an approach that allows you to sample exactly, even from very large wave functions, without even storing them. The problem with this approach is the same problem mentioned also this morning, and it basically happens every time this Hamiltonian does not have constant in-sign matrix elements. And unfortunately, this is the case, for example, for electronic matter, for chemistry, for a lot of interesting applications. So in this case, this approach, even though if it's very influential and it's been useful for a lot of things, for example, for fermions, would break down, and you would need the extra approximations. Now, another approach also sketched up this morning is about using the fact that typically these states can have a lot of a small amount of entanglement. So, for example, in 1D, there's a very interesting and extremely successful idea that is called the matrix for the states representation. So this is basically the idea that you have this huge vector psi, and you factorize it as a product of smaller matrices of size D. And this factorization, you can show that is basically exact for physical systems in one dimension. So in this case, you manage to map, to go around this exponential complexity, doing this simple factorization and using the fact that there is typically low entanglement in the ground state of physical systems in 1D. A problem with this approach is that if you go to two-dimensional systems or even to continuous space systems, things become quickly more complex. And for example, in 2 dimensions, we don't have an efficient, meaning not exponentially scaling technique to do the same kind of factorizations. Now, the third way around, which is also very popular these days, right, that people have been talking about a lot, is to use quantum computing, right? So you have this problem, we have this complexity of the wave function, so we don't want to store it on our favorite quantum classical computer. We want to use physical qubits to store the state of the wave function, right? So in this case, it's clear that this is the best thing you can do. It's optimal in the sense that you would have a scaling of the hardware which is linear with the number of qubits, with the number of electrons, if you want, right? However, there is a problem which is not always stressed, I would say, that even if you had the most perfect quantum computer, finding the ground state is still an exponentially complex problem. So there is no way, even if you have a quantum computer, to find the ground state in polynomial time, right? So it's clear that even in this case, and with all this way around that I've considered, there are cases where these are particularly helpful to solve some of the problems, but still the quantum many-body problem is there, has been there for since the beginning of quantum mechanics, and it will be with us, unfortunately, maybe for other 100 or 20 years, who knows. It's really a complicated problem where we need to have some techniques, a lot of techniques that are able to attack it. Now, the idea that I would like to present today is what we've been doing since 2016. The paper was published in 2017. This was in collaboration at the time with Matthias Streuer, who is now at Microsoft. And the idea is what I call neural network quantum states. So again, we have this wave function, this monster, high-dimensional monster in principle, but what we can do, and then what people do also for when they parameterize probability distributions, but in this case it's analogous. We want to find a compact parameterization of these objects in terms of neural networks, right? So we take a generic, for example, in this case, deep neural network that are parameterized in terms of these filters W and these nonlinear activations G, and basically the goal of this neural network as a parameterization of my quantum state is to compute the amplitudes of my wave function. So basically these coefficients C, up, down, up, etc. for an arbitrary choice of these quantum numbers that I was discussing before at the beginning. So the idea is that we have a variational, if you want, representation of the many-body state, where my variational parameters are now these W's typically, or even the structure of the network is itself something that you have to take into account. Now, from a technical point of view, this is typically just a standard deep neural network. However, there are at least the first complication is that typically we are interested in complex valued wave functions. So these are the most general states that you can represent in quantum mechanics. So for at the beginning of this story, we started like playing around with complex weights. So basically, we just used the normal neural networks, standard neural networks, but with complex weights in a way that you could have just a single output that would correspond to the amplitudes of your wave function. So this was our initial choice. We still do that a lot these days, but people and also us are also exploring also other kind of parameterizations where instead of having a single output, you would have like two outputs where one is basically the modulus of the wave function and the other one is the phase. So in that case, you could take like real valued weights, but a network with two outputs. So those are all equivalent parameterization to a sense, and it's not clear if in principle one of the two is best. It's just that personally I prefer the one with complex weights, but this is a matter of taste. Now, there are three main research lines that I will try to discuss today. So actually, I will mostly focus on the first one, which is about simulating quantum systems using this technique. Then there is there's another research line, which is also about somehow benchmarking quantum hardware. And then there is also somehow the theory of these neural network states. But again, for time reasons, I will concentrate mostly on this framework where we would like to simulate quantum systems. And but however, the learning framework that is somehow common to both data-driven and somehow simulation-driven approaches is really mathematically well-defined, relatively simple. It's basically an expectation minimization problem from, let's say, a machine learning perspective, where your loss function is something that the thing that you want to minimize depends on your weights in the network. And typically what you want to do is that you want to basically minimize the expectation value over some probability P of some, let's say, per sample loss L, right? So now this is very familiar, I guess, to all of you. But there are basically two scenarios in which we can use this approach that are somehow they make the distinction between simulation and data-driven approaches. So a data-driven approach is the case where typically this probability is fixed and is given by, for example, experimental measurements of a quantum systems. So it's something that is given by the external environment, right? So the tomography problem that was mentioned this morning is one of those examples where basically those would be experimental measurements from the quantum device. Then there is a simulation-driven case, that is the one I'm going to discuss more in detail now, that does not need external data. And in this case, typically the probability you sample from is the square modulus of this wave function, which is a probability by definition. You will notice that this probability will now, you don't have any external data in the sense that the probability you are sampling from is not stationary and is somehow self-consistently determined during the minimization of this quantity. So it's a more complicated learning framework than I would say the unsupervised learning that you would have when you have a fixed data set that allows you to somehow fix this P a priori at least. So just to give you an idea, this is a list of the applications that we can do with this approach. I won't go through this, but just to mention that we can frame a lot of interesting applications in quantum dynamics, for example, finding the ground state and excited states in terms of this learning framework that is described, but also doing unitary dynamics and simulating quantum circuits. For example, we did this in this paper, but also simulating dissipative dynamics, etc. So basically, all the applications in quantum mechanics can be phrased in this simple expectation minimization framework that I was showing you before. So let's go, for example, to the case of the ground state. So again, I want to find a good approximation for the ground state of a given Hamiltonian H, and you know that typically what you can do is that you can use a variational formulation of this problem to find this state psi here. So here I'm using all over the physics notation for brackets. I hope you are familiar with that. But basically, what I've written here is the Rayleigh quotient for the Hamiltonian in mathematical terms. So which is nothing but the expectation value in physical terms of the Hamiltonian over a given fixed variational state with weight W. And basically, you can show that this object is always larger or equal than the exact ground state energy. So basically, what we do here in this variational formulation is that we try to minimize this object to the best of our possibilities and then trying to find an approximation of the ground state. Now, the interesting part that was already noticed actually by Macmillan in the 60s is that you can rephrase this quantum optimization problem as a statistical expectation minimization problem, where you basically write this loss function, so basically this E and L are now the same thing, and you basically rewrite the expectation value of the quantum Hamiltonian as the expectation value of an object that we call the local energy that depends only on psi and on the Hamiltonian, and it's efficient to compute, over this quantum probability distribution psi squared, so this Born probability distribution, if you want. So the idea is that we can rewrite everything in terms of these expectation values over this classical, of this classical probability distribution. And the other important thing is that also the gradient can be rewritten in terms of expectation values over this high-dimensional probability distribution. So basically, this variational learning thing works as follows. At each step of the optimization, you sample a lot of samples in your batch according to this probability distribution, which is parameterized by your favorite, if you want, generative model. And then, using this batch of samples, you measure this local energy that allows you to have an estimate of the expectation value of the Hamiltonian. So the local energy is averaged over these samples. But also, using the same samples, you can estimate the expectation value of the gradient of the energy, which can be, again, also written very efficiently in terms of correlators over these samples that you've been drawing, for example, with Markov chain Monte Carlo. And what I'm defining in here is, okay, is nothing but the derivative. Yeah, it's written here. It's basically the derivative of the log of the wave function with respect to my variational parameters. Okay. Are there questions here? Yeah.
So what are what are the tone right
Here, this is the definition of the local energy. So this object that I was introducing before. So basically, the local energy. So sigma is now these numbers here. So it's the ensemble of the n, if you want, binary numbers. And basically, to compute the local energy, you have to sum over all non-zero matrix elements of the Hamiltonian sigma prime that connect to sigma. An important, very important fact is that for all physical Hamiltonians, the non-zero matrix elements here is polynomially large. So you can compute this object very efficiently. I mean, not very, but you can compute it efficiently. Yeah. Now, an interesting part, I mean, let's say from the, more machine learning perspective is that while people have been doing these things, so basically minimizing the energy stochastically for a long time, basically there's been never a strong connection with the standard machine learning literature. And indeed, there has been the development of typically the same or almost the same optimization schemes in the two communities. So let's say in the community of the variational Monte Carlo, which is the thing that I've been discussed, and in the standard machine learning approaches. So for example, the technique that we typically use to minimize this energy is not the standard gradient descent, stochastic gradient descent, but we typically use second order approaches, and we use a version of the natural gradient, for those of you who are aware of this, that has been developed independently. Actually, this is an older paper, but it's been developed at the same time as the natural gradient in our community by Sandro Sorella. And basically, this approach is a way of minimizing the energy, where instead of using just the gradient as you would do in standard SGD, you precondition it with a matrix that is not an approximation of the Hessian in general, but it is an approximation of the Fisher information matrix. So this gives you somehow a speed up, because you are going to to use a lot of metric information and go in the directions that are more important to minimize the energy. And this is, very well known in our field. I mean, typically we use it a lot, and we never use first-order optimization schemes for some historical reasons somehow. Now, so we've used this approach to do several things, but there's one application that, two applications that I would like to discuss a little bit more in detail today. So the first one is about frustrated spins, right? So I've told you at the beginning that two-dimensional systems are typically complicated to study with, for example, matrix product states or tensor networks, and also that there are families of Hamiltonian for which you have some problem and you cannot solve exactly. So this is precisely one of those Hamiltonians where you have some problem, so you cannot solve it exactly with quantum Monte Carlo, and that is hard to study with tensor network approaches. And this is a relatively simple model, which can be thought as the limit of the upper model, if you want, in the limit of large interaction, to some extent. And basically, you have two kinds of interactions in this spin Hamiltonian. So basically, you have a spin exchange at first neighbors along these black lines in the square lattice with this J1 strength, and you have another spin exchange term along the diagonals of this square lattice, right? So the interesting thing about this model is that, since it's somehow hard to solve, there is a debate whether this spin model supports a spin liquid phase, so which is basically a disordered phase that should, according to some theory, intervene between an L-order phase. It's when this J1 term dominates, so where you basically have up down on these links, and a striped order that instead appears when J2 dominates over J1, so where you would have like this columnar-like order, all up, all down, all up, all down, right? So the question, which has been open for 20 years, is basically, do we have this intermediate spin liquid? Now, what we did is that we tried out our approaches to this complex problem. So this is the paper where we started doing this. We use, again, a relatively standard convnet to represent the wave function. We use a 6-layer, in this case, of very, tiny, deep neural network. And the interesting thing is that you can make these answers, as you know, immediately translational invariance, because you take these filters to be, to impose translational invariance, so you can automatically, for example, study systems with periodic boundary conditions, and you have a nice set of properties that come along with this convnet structure. So just to give you an idea, so if you look at the error that you make on the ground state energy, so this is the relative error. Sorry, it's not written here. So in the first papers where we studied this thing with the RPM, so basically an RPM is just like a very obsolete neural network where you have one layer, hidden layer, and a fixed activation function, which is a log cosh. You can derive it analytically, but still with an RPM of varying sides, alpha, the error could go down already and improve some of the, at the time, existing state-of-the-art results using tensor networks. But then again, using this convnet, so a little deeper this year, we've been able to further improve upon this result. And this is the limit when, when J2 is equal to 0, so where we have some benchmarks to benchmark against. And then, using an actual deep network that I'm going to describe a little bit more in the following, we are able to basically solve this problem exactly to an accuracy of 10 to the minus 5. So we see that clearly, of course, but the non-trivial thing is how to use these networks efficiently in this kind of learning framework. But again, we see that if you use deeper network, we really improve on the energy, and we can improve quite substantially over other approaches. So this is the limit where we can benchmark things. Now we go to the limit where we don't have other exact results, but where we have other variational approaches. So the best thing that we can do is that we can compare our energies with energies obtained with other techniques and see which energy is somehow lower. And we somehow claim that if our energy is lower, also maybe our understanding of the physics is better. Now, this is the case where we could compare, for example, with an approach, standard, let's say, variational Monte Carlo approach devised by Federico Beck and co-workers, where they use a Pfaffian wave function. So in this case, these are the green lines, and this is the energy that, with respect to our convolutional neural network. So basically, if these points are in the upper part of this diagram, it means that our ansatz, so this NQS ansatz is more, is better, so it has a lower energy. Otherwise, it means that it's worse. And you can see that for, I would say, most part of the phase diagram, we have improved upon these 20 years old or something numerical studies, and where basically people have tried out different ansatz to study this problem. There is still a region in the middle that immediately is not still yet the best for us, where the emerging results are still performing better. But this is a region where we are suffering particularly about the breaking of SU2 symmetry. So one of the things that has been all over discussed, I guess also during this conference, is that in physics we really care about symmetries and we find in the networks that we are using. And this is also the case with us. So we see that in the middle, where we have the worst energy, I mean, comparatively, it's also the case that we are breaking one of the intrinsic symmetries of the problem, this SU2 symmetry, and we are aware of that, but there has been recently a way to somehow impose this SU2 symmetry and also more complicated things in these neural network states that has been published as early as May. And I believe that using this kind of ideas, we can also improve even further and somehow, hopefully, put a final word on this model, even though it's pretty complicated. Now, the thing that I wanted to discuss, which is actually somehow interesting from the machine learning perspective, is somehow, I mean, I told you at the beginning that if we try to use deeper networks, we can improve the energy. I've shown you really that if we go deeper, we can improve the results. However, I mean, up to this paper, I would say we had always used the standard variational Monte Carlo scheme, where you do a Markov chain to sample from your complex variational state, and then you use the samples over this, use a metropolis sampling that is somehow the standard approach to this problem. However, I mean, and somehow incorporating the nice ideas from generative modeling, we realized that it is possible to devise, for example, models from which you can sample from exactly during the variational Monte Carlo step, and that would allow us also to remove this costly Markov chain step that you have to do in the standard variational Monte Carlo approach. So the idea is that what we generalize the standard autoregressive models that people use to model probabilities, so high-dimensional probabilities. So in the case of probabilities, here you would have a P of S1 up to Sn, and you would factor this as a factor of conditionals, this Ci and P for probabilities, and you would parameterize each of these with a neural network, basically, with these autoregressive properties. But we have generalized this idea to the case where we are not normalizing these guys, so here, these conditional probabilities, as if they were probabilities, so they are not normalized in L1 norm, as you would do with a standard conditional probability, but they are normalized in L2 norm, right? So in the sense that the sum over S prime of psi square of these conditionals, pseudo-conditionals, is now equal to 1. So as a consequence of this different parameterization, you can show analytically that also the resulting total wave function is automatically normalized to 1, and you can also sample from it exactly. You don't have any autocorrelation times, and you have a lot of beautiful properties coming from the fact that this is a really truly deep network that you can optimize pretty accurately. So just to give you an idea, we see actually an improvement due to direct sampling. So this is a 20 by 20 spin model in 2 dimensions, a transfer Ising model. This is the error that we have on this model, and you can see that if we use direct sampling in a region where standard Markov chain Monte Carlo would have ergodicity issues. So this is the case, for example, when you have large ferromagnetic domains that you are not able to decorrelate fast using local moves. Instead, if you have a direct sampling approach, also the quality of the energy, final energy that you get is is much better than what you get with standard Markov chain Monte Carlo. And also, we are really entering into the region where we are starting to use, networks that are closer to the state of the art in terms of number of parameters and in terms of the depth that we are using here. Okay, are there questions up to this point?
So here, how do you train this autoregressive model?
Yeah, so the training is similar to the standard. What do you mean? You mean like what algorithm? Yeah.
Generative model.
Yeah. So here we use. Okay. So I work with computer scientists, so they refuse to use the natural gradient. I mean, they refuse to use the stochastic. So they use the ADAM in this case. But we tried out also KFAC and other things where you have this.
No, what I mean is the loss function.
No, it's always the same. So the only thing that we are changing in the VMC loop is the sampling part. Okay, I didn't write it, but so basically the way we generate samples from chi-square is the only difference here. So here we normally you would use local spin flips or some form of Markov chain Monte Carlo with Metropolis, accept and rejection. Instead here, in the other case, we do direct sampling, exact sampling. But all these steps are exactly the same. So all the gradients is always estimated as the expectation value over chi-square of these objects. It's all the same.
But you have to train the autoregressive network to do the direct sampling to the correct distribution.
No. That's the point. That's the important difference. So because here we have the freedom of parameterizing the distribution we want to sample from.
Okay.
So we do. So in this sense, we just parameterize it in this form, and then we sample from it exactly. So it's different from I would say the kind of applications that you do. For example, in the sense that we don't have a target distribution. Our distribution is changing dynamically during the optimization. So that's why I was mentioning in the beginning that the P depends now on the parameters. You see. So this is the difference with unsupervised learning, if you want. Yeah. So this is, I mean, Juan does not agree, but this is closer to somehow, let's say, reinforcement learning-like things in the sense that your probability is really changing.
So the wave function ansatz psi and the ability to sample from chi-square is self-consistently somehow they will evolve together.
Yeah, exactly. So the probability you are sampling from evolves during the simulation.
Okay.
Yeah. Yeah, okay, sorry, I spoiled it.
How much the way your training converges depends on how you initialize the parameters?
Yeah, okay, so this is, so in this case, yeah, you have to be careful. So what you can do is that you can do a pre-training on smaller system and then try to use the same filters on larger systems.
So you can sort of transfer learning?
Yeah, from small to large system, this is something pretty effective. But yeah, I would say that especially in the deep case, the initialization is a bit trickier than the standard case. But again, we have not developed, all the intuitions that people have in the standard deep learning applications. So I think that there's a lot to do here to improve this. Now, fermions. Okay, so this is the second application, something that, it's somehow very active these days. The problem with fermions is that, until now I've described the case where we were dealing with just spin degrees of freedom. So in this case, there's no special symmetry in the wave function that you have to require. However, when you have fermions, I mean, let's say that you have an electronic wave function, you have to impose that your state is, when you exchange two particles to fermions, the wave function has to pick up a minus sign in order to accommodate the Pauli exclusion principle. So this is a symmetry that you typically don't have for cats and dogs in machine learning because those are bosons, not fermions. So typically you have to somehow come up with a way to impose fermionic symmetry in cats and dogs. So I mean, one of the early approaches to this thing was what I call a super Jasov approach in the group of Imada in Japan. So basically, the idea here is that you multiply, let's say, a Slater determinant that takes into account somehow the anti-symmetric nature of the wave function, with a positive definite, for example, RBM in this simple case, that somehow does not change the total exchange symmetry of the wave function. So this is a perfectly legitimate approach of imposing this exchange symmetry. The drawback of this is that since this NQS is taken to be positive, you cannot change the nodal structure, so basically where the wave function changes sign. And this means that even if you increase alpha, so if you increase the size of the network, you cannot converge exactly to the ground state of the problem you are studying. So this was a benchmark on the Hubbard model in 2 dimensions, and you can see that extrapolating alpha to 0 does not allows you to really have an error of 0, or because of this reason. Basically, the ansatz you are working with does not allow you to extrapolate to the exact result. Now, more recently, there has been another interesting idea, which is basically the idea, instead of somehow multiplying your determinant with a correlator that is a neural network, you can do better, and you can change your orbitals using somehow what is called in literature a backflow. So basically, it's a parameterization of the orbitals that, so basically the orbitals that you put now in your determinant or in your determinants do not depend only on a single particle, but depend on the all particles. And you can take this object to be symmetric with respect to exchange of particles. So this is much easier to parameterize. And if you put these objects inside a determinant or more determinants, you can at least conceptually approach the exact ground state, because you can change systematically the nodes of the fermionic state, right? So this is an approach that somehow is already discussed in this paper by Markus Holtzmann and co-workers, and it is discussed in more detail in this approach in this paper by Brian Clark and Diluo, and it has been somehow also explored more systematically, I would say, in the context of quantum chemistry applications. There's a first work that came out basically less than a few weeks ago from DeepMind, and then there's a work from one of our organizers, Frank Noé, that came out also 1 week ago or something like that. So basically, you can see in this approach, this is a figure from the paper, the DeepMind paper. You can see that increasing the number of determinants, so here they're benchmarking against coupled cluster results, that is the gold standard for, for quantum chemistry in this case. So they say that somehow increasing the number of determinants, they improve the energy on these 2 diatomic molecules, not quite to the levels of a coupled cluster, but relatively close, probably within chemical accuracy in this case. Now, what is our approach to fermions? So, of course, we were working also on fermions for a long time, but we are now somehow we are ready to somehow discuss this approach a little bit more. This is a paper that is going to be out on the archive on Tuesday. Next Tuesday. So the idea is simpler in some regards, and the idea is that we just use basically a discrete basis set, like people normally do in quantum chemistry when they do not use an approach in continuous space. So we use so some basis set that, for example, is a Gaussian basis set, or anything that your favorite quantum chemistry package can automatically return, more or less. And then once we have a fermionic wave function, so a fermionic Hamiltonian, so here we are working directly in second quantization, so the fact that these guys are fermions is encoded in basically in the commutation relationship of these operators C. And what we do is that we map these fermions onto spin problems, because we like spin problems, and we've somehow gathered a lot of information about, I mean, we are getting better and better at solving spin problems, so we want to map these again into a standard spin problem. So there is a standard way of doing that, which is the Jordan-Wigner mapping, that I'm going to discuss in a second a little bit more in detail. But we've explored in this work, especially because we were collaborating with IBM people that are used to using these techniques for quantum information. We also tried out some other mappings, like the Bravicki type mapping that has the advantage that the kind of effective spin interactions that you get are not embodied as you would get for the Jordan-Wigner, but they are just order log n, where n is the number of particles. Now, the standard, maybe most familiar Jordan-Wigner mapping is the following. So basically, you map this C, so these fermionic operators, into a sigma minus, so basically a lowering operator in the spin language. And the same thing, I mean, and the dagger, the version of this for the C dagger and the sigma plus. And you, in front of these guys, you have to consider, however, that there is now a so-called Jordan-Wigner string that is the product of sigma Z operators. So basically, when you exchange two particles, you have to add, you have to consider how many fermions there are in the middle. If there is an odd number, you will get a minus sign, otherwise you will get a plus sign. So this is an effective way of mapping, again, spins to fermions. This is somehow standard. You will find it in any textbook of quantum chemistry, but also of many body theory. But the important thing is that effectively you get a spin Hamiltonian you can work with, which is effectively the sum of product of Pauli operators, right? Where these h's are just real numbers. Now, to give you an idea of what we've been doing with this approach, we've studied this couple of diatomic molecules too. So this is C2 and N2. So these are results in a minimal Gaussian basis sets. Because we wanted to understand how well we can capture correlations in this kind of molecules. And we use, again, our favorite simple-minded RBM with very few parameters. What I'm showing you here is basically the dissociation curve as a function of the distance. So this is the distance between the two particles, the two molecules, the two atoms, sorry. So you can see that typically our approach is, on this basis is pretty accurate. So these green points are the RBM results, and they are very close to the full CI, so the exact result that you can get on these molecules, which are the red lines, and they are typically better than the CCS DT, so with triplets, which is instead this line here, right? Okay. So the Jastrow ansatz is not plotted, but it would be higher than around here. So the same thing happens also for N2. You get pretty accurate results, and you improve also in this case even more, maybe in this case, because of the nature of the correlations in this molecule. You improve upon the couple cluster results on this again in this basis set. Now, yeah, you can see the numbers here. So basically, these are our results, the RBM results. We've studied up to the water molecule, and you can see that. I mean, I can tell you that basically on these molecules, small RBMs. Small means that where you have a number of parameters which is of the order of the square of the number of electrons. Basically, you get an accuracy which is well within chemical accuracy again in this basis set.
When you write Jastrow, that means variational Monte Carlo with a Jastrow?
Yeah, it means a Jastrow ansatz in this determinant space.
On the Archifock or on a multi-determinant?
It's in this second quantized version. So basically, you have correlations among determinants. So another advantage that I didn't mention of this formulation is that typically it's very easy to get I didn't write, but it's easy to get the Archifock state because it's just one of these configurations that you have. So you and we can represent that exactly. So, and then it's all the correlations that we get are somehow on top of the standard Archifock. And I mean, to quantify that, for example, you can plot the probability. So this is like psi square, if you want, in the basis of these determinants that we are using. And you can see that basically the exact wave function, which is this blue, which is the all blue thing here, has support on a few determinants here that are somehow the most likely, that correspond to Archifock plus a couple of excitations. But there is also a very important support on a lot of other excitations, and actually this one that somehow give you the chemical accuracy, not too much this guy. And it's important that your method can capture also this somehow tail in the wave function. And you can see that the RBM can capture this tail as, for example, opposed to this is a simple wave function where you have just singlet and doublets in on top of the artifact. So it seems that we are able to somehow capture more complicated correlations. Okay, this was more for fun, but we studied also the effect of using different mappings, because different mappings can also lead to different wave functions, right? In terms of complexity, also it's non-trivial that, for example, the Jordan-Wigner is the best of the mappings, but actually, for some reason that is still not clear, for us, the Jordan-Wigner typically leads to the best results in terms of accuracy, and the other more complex but more local mappings do not have as good as energy, even though they are still pretty accurate on these models. So something which is important to recall here is that we haven't solved quantum chemistry, not yet, but we have to be careful again when going to larger molecules and larger basis sets. So this is the open issue, if you want, of this technique that would be interesting to would be really interesting to address in the following. So, for example, if you go to a larger basis set, this is the case of water. I think I don't remember if this is double Z or some, yeah, I have to check, but it's a larger basis set than the Gaussian that I showed you before. Basically, what happens is that if you do standard Markov chain sampling in this basis, you get something which is terrible. So basically, you would have 0.1% acceptance in this basis, and this is due basically to what I was showing you here. So the fact that you have a few states that are really dominating the dynamics of the sampling, and accessing these states is like sampling rare events in your probability distribution. And if you do uniform sampling from psi squared, is really absolutely terrible if you have a very large basis. But this is how it is. We will address this problem, I guess, in a follow-up work. But the important is that I guess that we can somehow, to some extent, alleviate this issue by increasing the sample size. So this is you can see that there's a dependence on the energy on the sample size that you use to do variational Monte Carlo. And this is again because with this acceptance, using 1 million samples means that you are taking not even 1,000 uncorrelated samples to compute the gradient. So that's why you cannot go. You need a lot of samples. So this is the honest limitation of this approach, but hopefully we can improve on it. Now, I don't know how much time I left, maybe not much. Yeah, so I think I will just skip this part. So this is more related to what Juan has been discussing this morning, this tomography approach where we want to reconstruct the wave function. Okay, I will just skip this part. I will tell you something about the theory of quantum neural network states. Specifically, people have been trying to understand in what cases these states are interesting and what are their advantages over other ansatz wave functions. Again, mostly for spin problems, so there is still a lot of activity to be done there for fermions, for example. But for spin problems in general, I mean, one can say that using deeper networks is typically more efficient from an entanglement point of view than using shallow networks, in the sense that at fixed number of parameters, if you have a deep network, you can encode more entanglement than if you were using a shallow network with the same number of parameters. So this is discussed in this paper here. There's also a lot of literature about the entanglement properties of these states. I'm just flashing a couple of references. The thing that I would like to discuss, at the end, is really that doing this kind of learning is for some, mostly technical, but also less technical reasons, not so trivial with existing packages. We've devised our own little software library, which is called Netcat. It's an open source project. It's written it's in Python, but written in C++. You can basically use it if you are interested in these kind of things. And hopefully soon we will also have the open source implementation of fermions available online. So I've given you somehow an overview of some of the progress. This is really the latest progress. It's even unpublished about using NQS to some challenging problems. I think that it's fair to say that we've already shown, us and also other people, that using this kind of ideas we can already improve upon existing state-of-the-art approaches. There is a lot to be done, especially for fermions, but also for Husserl spins, especially in understanding how to use efficiently deep networks in variational learning. This is a wide open issue, I believe, and we've just scratched the surface with the existing applications. So most of our things are done with RBMs, which are not, the latest developments in the field, but there's a lot to be done there to really improve upon the existing approaches. And from a complexity point of view, this is something that I always say it would be interesting to find also a measure of the complexity which goes beyond the standard measure that people have in quantum information, which is entanglement entropy. So entanglement entropy is not really relevant for a measure of complexity for neural networks, and there should be some other measure, for example, related to sampling complexity, that people might find more convenient to describe the complexity in simulating quantum states with this approach. So the last slide is that we are hiring at CCQ, so we are here in Manhattan. And if you are interested in a postdoc position, also higher level positions, this is the website, and we are the Center for Computational Quantum Physics, and we are open to the latest advances in all numerical techniques, not only, of course, machine learning, but also tensor networks, DMFT, etc. So if you are interested, please apply. Thank you.